Okay, we started? Okay. So, last week's lecture, I got into some ill-informed speculation about how algebraic geometers use the terminology classifying space. Compared to how they use the term moduli space. And this came up in particular in connection with a description that I had heard, a sort of characterization of projected in space. As the classifying space for line bundles generated by n+1 sections. So I heard this description of projected n space. I heard it in a sort of introductory context, where it was evidently intended to be somewhat helpful and self-explanatory. And because, I mean, there wasn't any other explanation given of it, but it wasn't very helpful and self-explanatory to me. So I spent a while trying to figure out what they meant by it, and the problem wasn't so much that I couldn't think of any interpretation to give to what they were saying. The problem was more that I could think of several different interpretations to give to what they were saying, and one interpretation was more like this, and one interpretation was more like this. And when I say one interpretation was more like classifying space, and what I had heard of classifying space, I really mean what I had learned of classifying spaces from homotopy theory. So naturally, I guess I was unsure whether the algebraic geometers were just borrowing the terminology and using it the same way the homotopy theorists were using it, or they have their own specialized meaning for it. Because the more I thought about it, the more it seemed like what they really meant by this concept of classifying space, they really meant a kind of moduli space. And but on the other hand, perhaps I shouldn't overemphasize how there's a contrast between these two concepts. The point really is that they're really very similar. And but before trying to emphasize how similar they are, I'd like to start mentioning some superficial contrasts between them. Sort of as preparation for trying to understand why the differences, the contrasts, are really very superficial, and that there's really a unified concept behind them. Maybe at some level it's even sort of obvious that there's a unified concept behind them. I mean, they're both, in some sense, special cases of the general concept of universal property from category theory. But they both have some sort of, at least this one has some sort of fancy extra, I think they both have some sort of fancy extra aspects to them that go beyond just the most simple concept of universal property. But well, so let me try and give some of the contrasts between them. So first of all, there's one very superficial contrast between them, which has to do with it's very superficial. It's just in the language, it's just in the way we talk about it, it's sort of in the way that the word is parsed, which is that when people talk about classifying space, they usually talk about a classifying space for bundles of some kind of thing. You know, so we say a classifying space for line bundles, meaning for bundles of lines in this case. Well, that looks like a line, but I mean that is a blank. Bundles of anything. And in contrast, when people talk about a moduli space, they don't usually, they could, but they don't usually use the word bundle. They usually just say the moduli space of those things. Well, you could, if you actually have an instant classification of lines, you could say a moduli space of lines, or maybe it would be of lines equipped with some sections or something like that. But that's one of the contrasts between these two concepts. But it's very much a contrast of language because, well, I think I already mentioned this last time, that the word bundles is superfluous in a way, in the sense that a bundle of things means a whole bunch of them parameterized by some parameter space, parameterized by some extra parameters. And on the other hand, everything in the universe is already so parameterized by parameters that we don't even notice and don't even think about that everything in the world is like a bundle. I guess the classic example, one of the classic examples is you, right? I mean, you make it of yourself as like one thing, but there are ways in which you're actually a parameterized object. So, for example, you're parameterized by time in a certain way. It's like a bundle of you. It's like your whole timeline through the universe. And that's one of the ways in which you're a bundle, and you're sort of aware of it. There's probably other ways in which you're a bundle, and you don't even aware about it. There's probably like, you know, multiple universes. There's a copy of you that exists in other universes, and you're not even aware of it. But that's a little bit of propaganda for why the word bundles is a little bit superfluous here. But there's more to it than that. How do I say this? Well, before I try to say a little bit more about that, let me list another sort of contrast between classifying space and moduli space. So, again, classifying space, it comes from homotopy theory, and it has to do with classifying things, or classifying maps or something, up to, or it has to do with keeping track of maps up to homotopy. Whereas moduli space tends to have to do with keeping track of maps up to equality. Which is a finer way of classifying maps than classifying maps up to homotopy. And well, there's some confusing aspects to this issue here that I'm not sure I completely understand. But well, I want to go back to this bundle issue for a moment. I want to try to make it really clear why bundles are really involved in this situation over here. So you might think that bundles are only involved in classifying spaces, but bundles are really involved in moduli spaces as well. And I want to try to make it clearer how that happens. So, what's the point? So, a really naive idea of a moduli space is that it's the set of equivalence classes that you get from the equivalence relation X is isomorphic to Y. But if that were all there to it, then you wouldn't really expect a moduli space. You would really just expect a set, right? I mean, there's no... A space is something with some sort of cohesive structure, some sort of glue that holds the points together. And if all you have is this equivalence relation of x is isomorphic to y, then you get a set of equivalence classes. But there's not a particular reason to expect that those equivalence classes, those points, will cohere together in any way, like the points in a non-discrete space. Whereas in fact, the moduli spaces that algebraic geometers are interested in, that we'll be interested in, they very much do get some sort of cohesive structure, some sort of glue that holds the points together. And that glue really comes from this idea of bundles. So let me sort of say what I mean by that. Well, so we have the idea of we have some sort of moduli space of models of a theory. That's a little fragment of our main slogan, our fundamental slogan of what algebraic geometry is about. And the way that's a little bit missing from this, which is, you can say the moduli space of models of a theory in an environment. Environment really just being another name for a theory. Environment being the name used for a theory when it's in the mood to be the theory into which another theory is interpreted. And this environment, this is an extra thing that can be varied. So you can have a single theory, but you could look at its models in many different environments. So it's that idea of variation of environment that's primarily responsible for the cohesive structure of a moduli space. For why it makes sense to talk about things like, in certain contexts, it makes sense to talk about things like a continuous path in a moduli space. And the idea is this, how does it go? It's like, well, let's try to use that example of what would be the idea of a continuous path in a moduli space? Where does the idea of a continuous path in a moduli space come from? So let's start and try to take that. So write it down here somewhere. Can I use a different portrait? So a continuous path in a moduli space is equal to this. Is approximately defined to be a model of the theory in the environment I think I'm going to do a special case here. Let's say, I'm going to assume that we're doing a dimensional theory. So for a dimensional theory, the usual environment for the theory to be interpreted into is an environment of lines, an environment of one-dimensional vector space over a field. But a continuous path in the moduli space is going to be a model of the theory, a model of the dimensional theory. So, make it a dimensional theory. there are analogous statements for other kinds of theories, but we haven't really gotten to very many other kinds of theories yet. So I'll do it again with dimensional theory now. A continuous path in the moduli space equals a model of the dimensional theory in the environment. In fact, maybe I should really say a continuous map from any space into moduli space is a model of the dimensional theory in the environment of line bundles over X. That's the approximate idea. If something is like a or you could also say it's like a bundle of models, ordinary models, meaning models over the usual environment, over X. They're saying a model of the theory in the environment of line bundles over X, that's a bundle of models over X. And that's the same thing as an X-parameterized continuous map into the moduli space. And that's how the concept of bundles is secretly just as much involved in the concept of moduli space as it is involved in the concept of classifying space. Now then there's this other issue of how classifying spaces have to do with looking at maps up to homotopy, moduli spaces usually have to do with looking at the functional quality. There's probably a lot of things to say about that, none of which very few of which I'm prepared to say at the moment. But, well, we did mention though how when you read this slogan, when I read this characterization of projective end space, it at first sounded to me like it was just, algebraic geometry borrowing a phrase, borrowing a characterization from homotopy theories. It sounded like something a homotopy theorist would say at first. But then when I thought about it more, and particularly thought about the part about generated by n+1 sections, I realized that if you read this characterization with a sort of categorified lilt in your voice, particularly when you get to this part about generated by n+1 sections, or generated by n+1 sections, that sounds like a property. But if you interpret it in this categorified way, it suggests that you should really think that you're talking about equipped with n+1 sections. And then that becomes structure rather than property. And then the moduli space, classifying those structures, is really what they mean by this projective end space being this classifying space. So, the important idea that I'm trying to get across right now is this idea that the cohesiveness of moduli spaces is primarily due to this concept of variation of environment. That you can interpret your theory not just into a point-like world, but you can interpret your theory into a parameterized world. And models in such a parameterized world are sort of bundles of models, which are also like continuous maps into moduli space. So that's supposed to be a little bit of help in understanding what the concept of moduli space is about. In particular, you might not have seen any reason for moduli space to have some sort of cohesive structure on it, like a topology or something like that. but I'm trying to indicate why moduli spaces do have a cohesive structure. So that can be an important aspect of moduli spaces, that they have a cohesive structure. They're not just discrete sets. But there's another very important aspect of moduli spaces that's about to come up with an example that we're about to try. And that's going to be another very important aspect of moduli spaces. And that's going to show up, but it's really going to show up because we're going to stop calling them moduli spaces. And we're going to start calling them moduli stacks. And so there's another story about another aspect of moduli spaces. But it's such a distinctive aspect that it actually changes the name from moduli space to moduli stack. And, well, again, there's probably a whole lot more things to say, but as we change the name from moduli space to moduli stack, you might also consider changing this name from classifying space to classifying topos. Well, there's probably a lot more to say about that, but I won't try to say it right now. So I'm going to try and do an example right now. And again, this example that we're about to do is supposed to help us to learn the concept of moduli stack. So let me go ahead and try and do an example now. Perhaps I can say that the example that we're about to do is not really our first example of a moduli stack. We've actually been considering a moduli stack all along, but I've mostly been calling them, or pretty much exclusively been calling them moduli spaces. Particularly, they really are stacks. But somehow the example that we're about to do right now is a particularly good example of a moduli stack. A particularly good example where you can really see the stackiness, so to speak, of the stack. So what I have here is another example of a dimensional theory. And one of the ways that we've developed for depicting dimensional theories is the method of drawing a sketch of the theory. So I'll try that right now. I'll try and draw a sketch of the theory. So what's it going to look like? I get confused over the way to draw it, but I guess draw it this way. So that's a sketch of the theory. So let me try to give a verbal description of the theory here. I'll say it's the theory of the line object L equipped with what? A sort of quadratic function and a cubic function.
Homogeneous, of course.
Say it again?
Homogeneous, of course.
Yeah. Although you can sort of put them together and think of it as one single non-homogeneous function.
Mm-hmm.
And in fact, maybe I'll say that. So it's equipped with a polynomial function of degree 2 and 3 mixed together. So we're going to have the moduli space of such things. I'd like to give a silly name to such things, just for convenience. I'll call them cubo-quadratic algebras. So we're dealing with the theory of a cubo-quadratic algebra in a given environment. And so I'm interested in the moduli space of cubo-quadratic algebra. Except that it's not going to be really this space anymore. We're really going to do it the moduli stack of cubo-quadratic algebras.
I'm glad you're conserving magic markers. We're broke around here.
So, it's really hard to get these. I've been trying to.
Well, that's why, yeah. So try to keep doing that.
Okay. So we would like to get a good intuitive visual geometric picture of what the moduli stack of cubo-quadratic algebras is. I mean, again, we're aiming for the stack. We're aiming for this more sophisticated understanding than just the moduli space. But you are allowed, if you want to just, get off the ground in visualizing it, you are allowed to think about the moduli space of these things. So that's what we're aiming to understand. We're aiming to understand the moduli space, or its more sophisticated version, the moduli stack of this kind of algebra. And I guess I'll give a little peek ahead to what the final answer should be, but then we'll try to pretend that we don't know. We'll try to pretend that we didn't cheat. We'll sort of try to calculate what the moduli space is. So let me say what the moduli space and/or moduli stack of these things is like. Well, so let me try to describe it this way. So this is a sketch of a dimensional theory. This is a sketch of a dimensional theory. But our basic facts about, or one of our very nice basic facts about dimensional theories is that they're really just the same things as graded commutative algebras. So it's helpful to think about this thing as a graded commutative algebra. So let's describe it as a graded commutative algebra. So we have graded commutative algebra. But graded by Z. Graded by the three abelian group on just one generator, because there's just one line object in the theory. And it's freely generated by elements of degree 2 and 3. I guess I'll try to get names for those things over here. I'll call that one X and that one Y. Except, oh wait a minute.
So L has degree -1?
Yeah, okay, maybe it's say degree -2 or.
Well, this is probably why you were worrying in the beginning about which way those arrows should
That's
go.
right, that's right.
It doesn't really matter, I guess, which is why it's impossible to decide what to do.
Yeah, I'll be sloppy about that. It may be that, but I'll leave it like this. But you have to check about whether I'm using some weird convention about how degree 1 would correspond to, I guess, sections of L inverse, is that right?
Yeah, so if L has degree -1, you're,
Okay,
everything
okay.
you
I
said.
hope I didn't get it too badly screwed up here. It's the kind of thing where it's not really that important, but you can get yourself really confused by doing it the wrong way. So, we're going to be iterated by elements x and y of respectively degree 2 and 3. So, so there's a name for this graded commutative algebra. It's called the ring or the algebra or whatever of modular forms. The graded commutative algebra of modular forms. And there's probably a whole bunch of words in mathematics that start out with the letters M-O-D-U-L, and they're probably not all related to each other. But in this case, modular forms and moduli stack definitely have a lot to do with each other. So, I mean, how did this algebra, how did this graded commutative algebra get its name, that's the algebra of modular forms? It got that name because it's really, really closely related to a particular very famous moduli space. It's like the moduli space of elliptic curves or something like that.
And you can think of those guys as differential forms on that moduli stack.
In
No, I guess
some
not
weird
quite.
sense of differential forms. Let's not worry about that too much.
Okay.
They're really more like sections of line bundles or something like that. But
Yep.
So see, the fact that this is called the graded commutative algebra of modular forms is a big hint about what the moduli stack, what the moduli space is going to be. It's going to be more or less the famous moduli space, famous moduli stack of elliptic curves in the end. But that's not how we're going to start out seeing it. We're going to start out seeing it a little bit different. I mean, we have to follow our rules of our game. We have to follow the rules of the game of the doctrine of dimensional analysis. We have a dimensional theory, and we have to follow the rules for that and sort of calculate the moduli space. And then we somehow have to reconcile that with the claim that this is secretly really the moduli space of elliptic curves. So really what we're saying here is we have a space or a stack that is a moduli stack in two apparently different ways. And you really want to reconcile those two ways. And that's sort of what we have to try to do here. So let me try to prepare us for that task of reconciliation. So I just want to sort of rephrase that question of how to reconcile things. Rephrase it in a way such that maybe some of you can imagine how the reconciliation can take place. So think about it. We're supposed to have an equivalence between the moduli stack of elliptic curves and the moduli stack of cubo-quadratic algebras. So it's sort of suggesting that there's some sort of secret equivalence between the concept of a cubo-quadratic algebra and the concept of an elliptic curve. And a cubo-quadratic algebra is some kind of one-dimensional vector space. It's a line equipped with some sort of polynomial function on it, a cubic polynomial function, not purely homogeneous cubic function, but a slightly non-homogeneous cubic function because it's got also a quadratic part to it. So you have to try to think of some way that you can functorially convert back and forth between elliptic curves and something that's equipped with a slightly non-homogeneous cubic polynomial.
Want to tell people what an elliptic curve is? A definition that
Well, we want to say
hopefully
something
makes it
about that. We
easy.
want to say something about that. In fact, we want to say that, in a way, we're doing something a little bit backwards here, but it actually makes sense the way we're doing it. In other words, an elliptic curve is itself, of course, an object that in algebraic geometry, the thing that algebraic geometry study. And so if we had more time, it would be great to do lots of examples where we study an elliptic curve from the point of view of our approach, where you can interpret an elliptic curve as being a moduli space of a dimensional theory. And we may even get some time to do that, I'm not quite sure. But well, we don't have to do it right now. Okay, let's just say a couple of semi-popular level statements about what elliptic curves are. So first of all, they're curves in the sense of the algebraic, the complex algebraic geometer's sense of a curve, which is a complex one-dimensional manifold, which is an algebraic space. And so complex one-dimensional, so that means it's like really two real dimensional. And the adjective elliptic, it turns out there's a bunch of ways of describing it. One way of describing it is that it's donut shaped. It's a torus. That's a real two-dimensional thing, but it's a complex one-dimensional thing. And you can imagine all sorts of different numbers of holes that other real surfaces or complex curves could have, but the elliptic ones are almost by definition the ones that where it's just a classic donut shape, a single donut with a single hole, so to speak. And there's lots of really special things about that particular class of curves. In particular, the fact that all of the so you get a torus by taking a whole flat plane and modding out by a lattice, modding out by a discrete abelian group. Right? You sort of wrap up a flat plane. You roll the flat plane up into a torus, which you can think of as modding out by a discrete abelian subgroup of lattice. And one of the things that means, I said modding out by the discrete abelian subgroup. I was alluding there to the fact that the flat plane is itself an abelian group under addition of vectors, and that means that the quotient thing is also an abelian group. So that's one thing that's very special about these elliptic curves. They are abelian groups. They're complex curves, and at the same time they're also abelian groups. And one of the reasons that's important is because when we make a category or a groupoid out of these elliptic curves, there are different ways that you can do it. But it will be convenient for our purposes probably to require that the morphisms between the elliptic curves be homomorphisms of abelian groups. They should be homomorphisms of the abelian groups. So that's a really sketchy introduction to elliptic curves. They're pretty famous and important, and so I'm not making much of an attempt to give much of a background on them. They are a big part of algebraic geometry in themselves, but it turns out that they're also a big part of algebraic geometry in that the moduli space of the elliptic curves is an important object in algebraic geometry. So, So that was enough of the peek ahead, the sort of cheating, look at what the answer is supposed to be. Let's try to go back to just staring at the description of the theory and see if we can get some idea of what the moduli space is like. So, I want to have some way to sort of draw pictures of a cubo-quadratic algebra so that we can sort of think about how to classify them and things like that. So, well, it's supposed to be a line object. You can do this over any field you want, but I've already hinted, I think, that the really classic example is when you work over the complex numbers. In some ways, at least, that's the really classic example. And we'll do that. We'll work over the complex numbers. And so a line is really, this is a line, a flat whiteboard, which is a complex one-dimensional object. And
so you're partway done.
What?
You're already partway done drawing it.
Yes. Okay. That's true. That's true. But for it to really be a line, you have to remember line means one-dimensional vector space, so it really should have an origin. So I should really put an origin. Okay, now that's a picture of a line. In this case, that's what a line looks like. It's got an origin.
Looks like a point.
No, that's fine. This is the line.
I'm just joking.
Okay. So, that's a picture of a line. But now we have to put the structure on the line. So, we want a polynomial function of degree 2 and 3 mixed together. What do you think of degree 2 and degree 3 separately, and then they're just added together? And
guess?
what?
Can I guess, or am I getting interrupting too much?
Well, let me try. So, let's see. How can you draw suppose we just try to draw the quadratic part. Suppose we want to draw a quadratic polynomial on this complex vector space. So, how could you do that?
I know.
What are you going to say? Yeah.
Just draw where it equals 1.
Okay, yeah, that's good. That's good. So I'll try using another color for that or something like that. So how many places and in what ways are they situated? Is this purely quadratic function going to take the purely quadratic complex polynomial function? How many places is it going to take on the value 1, and how are those places going to be situated?
I've done my work for the day. 2 points?
2 points, yeah. And how are they going to be situated? Yeah, they're negatively set. That's part of the property of being homogeneous quadratic, that you take on the exact same value. Those are supposed to be the exact same distance apart, but that's supposed to be exactly opposite. So that's what this structure is supposed to look like. And then I should turn it into another color for the cubic part. So how are we going to draw the cubic structure here? How are we going to draw the cubic? Okay. Yeah.
They're going to be some complex number times the cubic root of the candy.
Yeah. So it could be kind of anywhere. It could be like out here, and then 120 degrees away from that. That wasn't a very good one, 120 degrees. Somewhere there or something. So that's sort of what a cuboquadratic algebra looks like. Although there are some weird degenerate examples that you might have to think about a little bit. So like, what does the picture look like if one of these goes to 0? Let's say x goes to 0. Where do the red points go as x gets close to 0? That's what I thought too, but you were wrong.
Oh, you're exactly wrong.
They go the other way, but
Point infinity.
yeah, they go to the infinity. And same thing, as the cubic thing goes to 0, the green points will go to infinity. So,
If you turned around those arrows,
yeah.
I guess then Chris would have been right.
Yeah, maybe, something like that, yeah. That's right, that's right. That's right. And, so, see, part of the point is supposed to be that when you draw a picture like this, the symmetry of the resulting object, the orthomorphism group of the resulting object, which is going to be an important part of the stack, the orthomorphism group of the resulting object is supposed to be sort of visually evident, or, depending on how good your eyesight is, it's supposed to be visually evident. Like you can, maybe in this example, you can sort of see that there's no symmetry. Is that sort of obvious? This picture doesn't have any symmetry.
You almost drew it so it has
Almost to the
bilateral symmetry.
Okay, but even if that were true, that bilateral symmetry would be illusory, because that would not be a complex orthomorphism. This is supposed to be a complex vector space. They have to, it's not visually obvious that you're not allowed to reflect it. You have to remember that you're not allowed to just reflect things. Those are real linear reflections, but they're not complex linear. So yeah, so we're really just looking for rotation symmetries. And I guess it's fairly clear that it's fairly clear that this hasn't got any of those. It hasn't got any rotation symmetries. So can you give me any examples of cuboquadratic algebras that do have symmetries? So to give.
So if you expand out either the red dots or the green ones, so they go to the point of infinity.
Yeah. Actually, before we do that, let me just make a comment here. I want to try to make a comment about what we're trying to do here in trying to figure out this moduli stack. A lot of what we're trying to do in figuring out the moduli stack, it has to do with understanding the morphisms between cuboquadratic algebras. And it turns out that all of the morphisms between cuboquadratic algebras are isomorphisms. So we're really concerned with understanding things about the isomorphisms between cuboquadratic algebras. And there are two pretty different things that we're concerned with about what the isomorphisms between cuboquadratic algebras do. So one of the things that isomorphisms between the algebras are responsible for is they're responsible for figuring out what the points in the moduli space are, figuring out what the isomorphism classes are. So you can have two apparently different models. Like you could have, we're going to try and draw two apparently different models. You have this one right here, and then you have another one, which think of it on a separate whiteboard, and it would look like that, and then like I was attempting to make this little picture look like a little shrunken picture of this, but still looking the same. Oh, but if I'd been better, I would have also rotated it by some amount. Because even if you rotate it, right, it'll still be isomorphic to this one. So the isomorphisms between the algebras are very important because they tell you when things that look different are really the same. So you have an isomorphism between different ones, it tells you that they're really the same point in the moduli space, or in the moduli stack. But it's also very important to think about isomorphisms not between different algebras, but isomorphisms between the same algebra, automorphisms of the algebra. Because that's the extra aspect of the moduli stack that the moduli space doesn't have. Okay? So there's really two important aspects that a moduli stack has. We already talked about one before, the fact that it's the cohesiveness of a moduli space. So moduli spaces and moduli stacks also have a certain cohesiveness. We already saw that when we were just thinking about moduli spaces instead of moduli stacks. We saw that by the concept of variation of environment, moduli spaces get a cohesiveness, a kind of glue that holds the points together. It lets you talk about continuous maps into the moduli space.
That's pretty visually evident in this example now. You can imagine varying that picture in a continuous way.
That's right. It'd be like animation, continuous animation of this picture. Like not rotate. They have to. Like watching the constellations in the sky change. Where they actually change their shape. You have to wait a long time for that. We don't have enough time for that right now. So I'm trying to emphasize that the moduli stack has two important aspects. One we talked about at the beginning, and one we're talking about right now. At the beginning, we talked about the cohesiveness of the moduli space. And that's still true for the moduli stack. But the moduli stack has this extra ingredient, which is that the points of the moduli stack, you keep track of them having automorphisms. Whereas in a moduli space, you don't really keep track of the points having automorphisms. I mean, it doesn't make sense for a point of a space to have automorphisms. But it does make sense for a point of a stack to have automorphisms. And at a somewhat low level of sophistication, that's what moduli stacks are about. They're about combining those two concepts, the concept of cohesiveness by variation of environment, and the concept of points having automorphisms. Because the points are really representing models of a certain theory, and those models have automorphisms.
We've got a person in the room who's writing a paper on topological groupoids right now, and that sort of combines those two notions. Right?
There are very interesting relationships. Okay.
So the topology and the presence of automorphism.
There's a lot more to say about that, but again, we're a little short on time. So John's suggesting that there are interesting relationships between moduli stacks and topological groupoids. There's a third thing you could throw in that mix as well. It's also very closely related to those things, which is again classifying topologies. But again, we don't have time for that right now either. We may get to that in a later lecture. So so you're really supposed to try to tell me about both these things. You're supposed to try to tell me about how to parameterize all the different isomorphism classes of models that we're getting. But also, for each of those isomorphism classes, you're supposed to try to tell me what the automorphism group is for that point. And that gives us somewhat of a naive picture of what the moduli stack is like. although at this point we're not emphasizing the cohesive structure. We're really just kind of like, you can put it this way, that the moduli stack is it's a whole complex of models of the theory. And not just models of the theory in one particular environment, but models in a whole bunch of different environments. So for each particular environment, you get the category or perhaps the groupoid of models in that environment. But then you can vary the environment, and so you're getting a whole functorial complex of groupoids of models of the theory in different environments. And that's kind of what the moduli stack is. But we're being a little bit naive right now. We're not at the moment varying the environment that much. We're mostly taking the classical environment. That's why we're just drawing complex one-dimensional vector spaces. We're just thinking about models in that environment. It's not giving us a naive picture of this moduli stack. It's really just a single groupoid. But that's good enough for now. So
I'd want to classify the zeroth approximation to classifying those isomorphism classes of models, which isn't really right, is to say I need to know the ratio of the size of the red picture and the green picture together with the angle that they're rotated relative to each other.
You can kind of say this. If all you had was the red structure, the quadratic structure, then almost all of the time you can, so to speak, gauge this. You can rotate the thing around so that it will look like that. Right? Because if you just rotate the red thing, you're keeping the symmetry of the red thing. Yeah, I mean, if you just rotate the whole picture, it's an isomorphism of the algebra. So if all you have to worry about is the red, then you can always just rotate it so it's like this. And then you have to consider where the greens are. And so the greens could be wherever. So it's like, so it sounds like John's first approximation is that after you gauge fix the reds, you have a free choice of where the greens go. They can go pretty much anywhere. I guess they can't go in the middle, I guess that's right. But they can go anywhere else. But when they go anywhere else, they have to go to the other 2 points as well. And then the other weird possibility is that the greens can go out at infinity. And then the other weird possibility is that the reds can go out at infinity. And in that case, you have to do your analysis of the greens all over again. So
so there are two weird points.
Yeah.
At least two weird points. There are two weird points. One where the reds have gone out to infinity. And one where the greens have gone.
This is the one where the greens have gone out to infinity.
Yeah.
And then there's the one where the reds have gone out to infinity. So those are special points in the stack, because those are the ones that really make it stacked. Because a typical one doesn't really have any orthomorphisms. So when you're saying these typical ones, it feels more like a moduli space than like a moduli stack. But when you get the models that have orthomorphisms, then it really begins to feel like a moduli stack. And it's a little bit pleasant in the way you actually get an interesting variety, somewhat interesting variety of different types of symmetry. Over here you get sort of bilateral symmetry, over here you get sort of trilateral symmetry. So, well, again, sheeting, we know that this is supposed to correspond to elliptic curves. And elliptic curves, you can think of these lattices in the plane that you might outside. So if you know that, then you must know that this must correspond to some sort of lattice that has bilateral symmetry of some kind. Well, bilateral, it has some sort of Z-mod 2 symmetry of some kind, in some sense. In some sense, it must have Z-mod 3 symmetry. And this must correspond to some lattice that has some sort of Z-mod 3 symmetry. And there are such lattices. the hexagonal lattice has this kind of symmetry, in some sense. For some reason, I'm not quite fixing it in my mind. I'm having trouble fixing in my mind why. Maybe just kind of draw the lattices. This is sometimes called the Eisenstein lattice, the hexagonal one. What does it look like? It's supposed to be equilateral triangles. They're forming a hexagon, and the lattice is up going like that. And that's the lattice that you roll up to get the torus. That's a very special lattice. It has more symmetry than the arbitrary lattices. It corresponds to this special point in the moduli space of elliptic curves. There's another very special one. There's a square lattice that has more symmetry.
So it's a little confusing because all lattices have some symmetry. And so you have to sort of detect how much more symmetry these have than the others. And this has Z mod 2 more than the rest.
Yeah, in some sense, I hope, if I didn't screw up, it should be that the torus ends up with just an extra Z mod 2 symmetry. And this torus ends up with an extra Z mod 3 symmetry. So, but again, notice we're combining the cheating approach with the honest approach here. The honest approach is when we think about these cubo-quadratic algebras. The cheating approach is when we try to exploit rumors that we've heard about elliptic curves and things like that. But let's see if we can try to make a connection here between the honest approach and the cheating approach. So,
about 2 minutes.
I thought it was just 5.
7.
I don't know. Okay.
Yep.
So, does anybody, John, do you remember? Well, I can give a sort of reference to one of John's this week's finds, where he discusses what's the connection between the cheating approach and the honest approach here. So, well, we'll say more about this later. But remember, you can think of a cubo-quadratic algebra as a line equipped with a slightly non-homogeneous cubic polynomial. You can use that cubic polynomial to get 3 special points on the line. The roots of the polynomial. Well, maybe say it this way. If you've done much reading about elliptic curves, you should know that there is a way to get an elliptic curve from a cubic polynomial. And it is, in some sense, functorial. And that's what's going on here. That's sort of the explanation for the relationship between these 2 different ways of thinking about the moduli space. You can think of the moduli space of elliptic curves or a moduli space of cubo-quadratic algebras. And there's a systematic way of getting an elliptic curve from a cubic polynomial. And this is secretly bad, but I'm not sure I have enough time to explain it right now.
Well, you can just say...
let me try.
Okay.
So there's a cubic polynomial. That gives you 3 points. There's another 4th point that you can get because, well, really, because you have a projective line, so there's an extra point at infinity instead of just having an affine line. So you actually get 4 points. You get a Riemann sphere with 4 points on it, and you try to cook up an elliptic curve from that. So yeah, I'm saying from this thing you can cook up a Riemann sphere with 4 points on it. And from a Riemann sphere with 4 points on it, you can take a double cover of the Riemann sphere. It's double covered at everywhere but the 4 points, but it's branch, so-called branch cover at the 4 points. And there's there are very nice geometric pictures of how that actually gives you an elliptic curve. And that is what's going on here, roughly. There's a lot more to say about that, but we'll have to sort of leave it at that for now. Let me just think if there's anything I want to say to try to sum up here. I think I still have 1 minute. There are things I want to say, but I don't have time to say it. I'll try to say it next time. But it has to do with this idea that a moduli stack, we're trying to learn what a moduli stack is, and we're trying to learn how to understand the two separate aspects of a moduli stack. It's got cohesiveness to it, like a moduli space does. Then it's got this extra aspect that points of the moduli stack. Unlike points of a moduli space, points of a moduli stack have automorphism groups to keep track of. And we'll have to, we're interested in developing ways of understanding this kind of object.